In this video, we are going to look at the examples in the Chapter 4, Section 5 slides. Our first problem asks us to find the number of significant digits in each of these numbers. We start with 5,205. Because the number begins and ends with non-zero numbers, it has each digit is significant. So this has 4 significant digits. Remember that leading and trailing zeros are not significant. So in this case, we've got 12,000. The 1 and 2, those are significant, but the 3 zeros are not. So this has 2 significant digits. In this one, we have 3 leading zeros and a 3, so it has 1 significant digit. Keep writing a D at the end of significant instead of a T. I don't know why I'm doing that. This one has a leading 0 before the decimal point and then 105. This has 3 significant digits. And this one starts with a 3, then our decimal point, and then 02. This also has 3 significant digits. In our next problem, we're asked to find the greatest precision and find the precision and the greatest possible error of the measurements. The precision is the smallest subdivision. So here, we're looking at something that's being divided into eighths. So the greatest precision here is 1/8. Here, we're looking at decimal in the tenths place. So the greatest precision, the precision here is 0.1, 1/10. The greatest possible error is 1/2 of the precision. So the greatest possible error is going to be 1/8 times 1/2, which is 1/16. And here we've got 0.1 times 1/2, or 0.5. And that's going to give us a greatest possible error of 0.05. Just 1/2 of 1/10. In our next problem, we're asked to find the absolute, relative, and percent error of this problem where a blueprint for a part calls for it to be 32.112 millimeters, but the measurement of an actual part is recorded as 32.155 millimeters. So the absolute error is just the difference between the observed measurement and the true value. So our observed measurement is 32.115. Minus 32.112. When I subtract that, I get 0.043 millimeters. That is my absolute error. For the relative error, we find the quotient of the absolute error and the true value. So that's going to be our 0.043 divided by the actual measurement, which will be 32.155. And if I plug that into a calculator, I get 0.001333727. We would probably round that to maybe 3 decimal places as 0.00134. Depends on what the problem is asking for. Finally, for the percent error, we take this, multiply it by 100, and put a percent at the end. So that'll be 0.134%. In our next problem, we're asked to add the measurements 12.5, 12.5 meters, 38 centimeters, 2.9 meters, and 43.225 centimeters, and to round appropriately. So when we're asked to round the sum or difference of measurements of different precisions, we need to change all measurements to a common unit of measure. So we'll change this to centimeters. We add or subtract the common units of measure, and then we round the results to have the same precision as the least precise measurement. So the least precise measurements are in these 12.5 meters and 2.9 meters. Those are the least precise because they go to 1/10 of a meter. We know that a centimeter is 1/100th of a meter. So this is 1,250 centimeters for the first one. 38 centimeters is still fine. 290 centimeters. All we have to do is multiply these numbers by 100. And 43.25 centimeters. Those are our measurements. Now we're going to add these up. So 12,050 plus 38 gives us, 1,250 plus 38 gives us 1,288 plus 290. Do this on calculator, that'll be the easiest way. 1,250 plus 38 plus 290 plus 43.25 gives us 1,621.25 centimeters. And then we need to round this to the nearest 10 centimeters, which is the same as the nearest 10th of a meter. So I'll round it to 1,620 cm, or 16.2 meters. Next. Next, we're asked to multiply these measurements. Now, and round appropriately. When we're rounding the product or quotient of measurements of different accuracy, we multiply or divide the measurements and then round the product or quotient to have the same number of significant digits as the measurement with the fewest significant digits. So here we have 150 meters, 105 meters, and 50 meters. And 50 meters has only one significant digit. So we're going to round to one significant digit here. We get 150 times 105 times 50, which is 787,500, and that's cubic meters. But we're going to round it to one significant digit, which means we're looking at 800,000 cubic meters. Now we're asked to find the distance between 2.5 and 4.5. And to find the distance between any two distances, all we have to do is subtract. We take the larger number, 4.5, and subtract the smaller number, 2.5. Well, the halves subtract, and we're left with, 0 halves. And then we do 4 minus 2, and that's just 2. So this is a distance of 2. Finally, here we're asked to find the midpoint between 2 points on a metric ruler at 2.8 centimeters and 5.6 centimeters. And to do this, we're just going to add these and divide by 2. That's our formula for the distance on a straight line. The midpoint on a straight line, it's the average of the values, or the mean of the values. So it's, midpoint M is equal to A plus B over 2. So here we've got M equals 5.6 plus 2.8 divided by 2. 5.6 plus 2.8, that's 7.0, which is 3.5 centimeters. That's not quite right. I'm sorry, I did that wrong. 5.6 plus 2.8 is in fact 8.4. So not 3.5, but 4.2 centimeters. All right, that's it for this video. If you have any questions, please get in touch.